Hi guys, welcome to your second video on chapter 24. We're looking at how the t-distribution can be used to talk about confidence intervals and hypothesis tests for differences between means, not proportions. Alright, so let's go ahead and check out the problem here. This is going to build so much off of the kind of, well, not really, but kind of new math that I showed you in the first chapter 24 video. So hopefully this is not like a stumper. Alright, we are told we want to know whether people are likely to offer a different amount for a used camera when buying from a friend than when buying from a stranger. I wonder whether the difference between mean amounts is 0. I bid prices from 8 subjects buying from a friend and 7 buying from a stranger, found in a randomized experiment. We've got the 8 different prices where a used camera is bought from a friend. We've got 7 prices where a used camera is bought from a stranger. Let's go ahead and show the mechanics and the conditions for completing a hypothesis test for difference between means, and take it from there. Alright, so first, to no one's surprise, with this being a hypothesis test, when you set up your hypotheses, remember, we are making claims about what population data is going to do, and your evidence is the sample data that has been collected from the randomized experiment. So we are not going to say the following. H naught is that X bar for the friends, the mean price that a used camera is sold at to a friend, minus the mean price that a used camera would be sold at to a stranger is equal to 0. Instead of those X bars, because we are making claims about the populations, we want to use μ's. Remember, Greek for population, Latin for sample. So we're going to say mu sub f, the mean price of a used camera being sold to a friend, minus mu sub s, the mean price of a used camera being sold to a stranger, should be equal to 0. That's what we're testing for. The alternative from the context, we said, second sentence, I wonder whether the difference between mean amounts is 0. So that leads us to believe that the alternative hypothesis will be simply that there is some difference, meaning this difference between population means should not be equal. That's the alternative we're testing for. Alright, so conditions. It is the exact same set of conditions that we had for a confidence interval that was set up for a difference between means. So we're going to follow exactly that same set of guidelines. Conditions here. We first want to check for randomization. And that one's not too hard. We were told the data was collected randomly. So we'll go ahead and write that out. We're told, well, really that we have a random experiment. We're told the data was collected from a randomized experiment. All right, no sweat. So there you've got the randomization condition knocked out. Let's go ahead and talk about the 10% condition as well. 10%. Sure, that one's met. We've got that 8 was that used camera sales to a friend, yeah. 8 used camera sales to a friend should be less than 10% of all used camera sales. Alright, not too bad there. So we talked about the first sample. Remember, we've got to compare both samples here. We will only make one comparison if there's only one sample that we're working with. We also have 7 used camera sales. Used cam sales to a stranger would be less than 10% of all used camera sales. Okay, so those 2 conditions are knocked out. We've got 2 more to look at. We need to see whether or not the independent groups assumption is met. Independent groups. And yeah, sure. I mean, if this is information taken from a randomized experiment, then because these are random participants in the experiment, hopefully there's no interaction between people who are buying from a friend or the person selling to their friend, versus in the second category, buying from a stranger or selling to the stranger. These participants shouldn't know each other. So, okay, we'll say that the independent groups assumption is met because the people making the sales and buying the cameras were random. Alright, last condition that we have to check. Remember, whenever we use a t-distribution, we need to check to see that we've got the nearly normal condition met. So we're going to check that next, nearly normal condition. In C. And yeah, we can check that very simply. I've already loaded up into Wabbit the data into L1 and L2. I'll show you that real quick. It's all set up and good to go. Next, don't forget, we need to make two histograms here, one for each different set of sample data. So go second stat plot. That is on. It's currently set to L2. I'll change it to L1. Yeah, we'll change it to L1. Enter that. Let's see how zoom stat works. Quit out of that. Zoom stat. Obviously, that's not unimodal and symmetric. The two things we're looking for, the sample of data to be. So we'll go ahead and go to Window, and then playing around earlier, what did I find that worked well? 250 to 325. 250 to 325. And that was in multiples of 25. Let's up the Y max just in case it was going to clip anything off. Enter that, and we will go to the graph. And that's better. We can trace that. 2, 3, and 3 for bin sizes here. Yeah, let's write that down. So this is L1 was my first row of data, so that's buying from a friend. So we can call this histogram here buying from a friend, as you might suspect. Buying from a friend. Okay, the horizontal axis, you've got the prices that these used cameras were sold at. So you got 250, 275, 300, and 325 with counts or a frequency here on the vertical axis that go from 1 to 3. So first bin looks like so, second two bins as follows. And yeah, that is more or less unimodal or symmetric, and symmetric rather. You've got one central bin here that is quote-unquote the highest. It is tied for highest with the one to its right. And to the left and to the right, you've got more or less equivalent bins. You've got count of 2 in the first tier, count of 3 in the second, but yeah, we'll say that those are unimodal and symmetric. Okay, second set of data in L2. Let's check this out and go into second stat plot. The only thing we're going to change here, the histogram is already chosen. We just want to change this list to be L2. Not a big deal. And let's zoom stat this to see how it looks. Really, that's pretty good. That is pretty good. Let's go ahead and use that. I mean, we've got one extra bin over here on the left, but for all intents and purposes, that's fairly unimodal and symmetric. Again, why are we checking for unimodality and symmetry here? Well, because the sample sizes are under 15. You've got sample sizes of 8 and 7. So you got to meet both conditions with your histograms. All right, let's call this second histogram buying from a stranger. Buying from a stranger. Okay. It looked as follows. We had on the low end $130. And we had 5 bins here. 1, 2, 3, 4, 5. Going 32.5 at a time. So this is 195. This would be 260. And this last one right here would be 292.5. Okay, so we had counts ranging from 1 to 2. And first 2 bins are both 1. Second 2 bins both 2. Last bin back to 1. All right, so let's finish this out. Remember that with the nearly normal condition, it's not just enough to make your histograms. You need to say that the condition is met because both distributions, both samples are unimodal and symmetric. The abbreviating here in NC is met because both distributions are unimodal and symmetric. Okay. All right, so we're done with the conditions on the mechanics here. I'll do this in blue. This is the heart of the problem. Again, remember the conditions here that we just knocked out, these four conditions, randomization, 10% independent groups, and nearly normal. We did these guys so that we could use the t-distribution at all. We can't automatically assume that based upon how the data was collected from this randomized experiment, other samples, let's say we ran the experiment the exact same way over and over again, we can't automatically assume that those results would also be constructed in such a way that we could organize them all into a t-distribution. Remember, the t-distribution showing us how all these differences between samples from hypothetical randomized experiments that aren't being run would look compared to each other. But because conditions are met, we can talk about these hypothetical results from randomized experiments that we are not running as being organized in a t-distribution. So we've got our bell curve, degrees of freedom. How do we get that? Well, easiest way I know of is to use the stat calc tests to sample t interval. That's really easy for finding the degrees of freedom. That takes, it can either take data or it can take stats. Now in this case we have not yet calculated x bar 1, x bar 2. That is the sample mean of the first sample, the sample mean of the second sample. We don't have sx1, the first standard deviation, sx2, the second standard deviation. So let's just go ahead and use data because we do have that set up in L1 and L2. The lists are good to go. Frequency's good. Confidence level doesn't matter. Just leave it at 0.95. Pooled, we are not going to pool in this class. I thought about introducing that. It's a fairly rare thing that we would want to do, and I'll get to why we don't here in just a second. Let's calculate that and see how many degrees of freedom it tells us we've got in our from the data. So 7.62. All right, we need that later to find the critical t-score. All right, so we've got the degrees of freedom. Now I'm going to write a few things out for you here, and I'll let you know where I got these, but I'm not going to show you that on the calculator. N sub f, the sample size of the people who bought from a friend is 8. Y bar, or yeah, let's stick with y bar. Y bar sub f, the sample mean here is 281.88. S sub f, sample standard deviation, is equal to 18.31. Okay, sample size for the stranger's sample was 7. That mean was equal to 211.43, and that sample standard deviation was, oh, I got a spider on my wall, 46.43. Oh yeah, where did I get these? I got all of these from using 1var stats and stat calc on L1 and then L2 respectively to get that data. All right, so what do we have so far for this t-distribution? Well, look back up here real quick with me. When we set up the hypotheses, we made an assumption about how the means of all the sales from friend to friend and all the sales from stranger to stranger with used cameras would look. We assumed that difference would be 0. So that's not too hard to talk about what we would expect, the expected value of y bar sub f minus y bar sub s to be, which should be 0. If we assume that the populations don't differ with respect to their means, we should assume that samples in general will not differ either, right? So we're going to set at the center of this t-distribution 0. Now, one thing that's going to differ here from when we built a a hypothesis test for the difference between proportions. When we built that for proportions, we had to talk about the standard error pooled of something like this. It looked like p hat 1 minus p hat 2, and we had to find the pooled sample proportion of success here based upon assumptions we made in the hypothesis test, or in the hypotheses. Here, though, your standard error calculation, if you remember from how we built confidence intervals, looks like the following. The standard error of y bar sub f minus y bar sub s is equal to the square root of the first sample standard deviation for friends squared over the sample size for friends plus the first sample standard deviation for strangers squared divided by the sample size for strangers. Cap off that radical. Notice nowhere in this standard error calculation does the assumption that we made about how the means differed, highlighted in blue there, come into play. So we do not have to pool because we're not violating the hypotheses that we made at the first step with our standard error calculation. So we can use the sample data. You don't have to pool. You do have to pool if you're talking about the standard error for the difference between sample proportions in a hypothesis test, but you do not have to for the standard error for the difference in sample means of a hypothesis test. Big difference, big important difference there. All right, so we've already got all of these standard deviations and the sample sizes. This comes out to be doing some plug and chug here. I'll write it out under the radical so you're seeing what's going on. 18.31 squared over the sample size for the friends of 8 plus 46.43 squared all over 7, sample standard deviation of the sample data from strangers squared over the sample size of 7. All of this comes out to be 1870. So we'll plot our standard errors on our t-distribution here. 1870, negative 1870. And what do we need? Well, we have mean, we have standard deviation. We don't know yet, I mean, it's not hard to find, but we don't know yet how the sample means actually differ. So we need to talk about where, let's do this in red, where on this t-distribution does the sample data fall? Does the sample data fall so far from the mean that it gives us evidence that our hypothesis, our null hypothesis is false? Or is our data going to fall so close to this mean that it looks like the null hypothesis is true? That's what we're looking to check for with our sample. All right, so we are going to say that y bar sub f, sample mean for friend sales, minus y bar sub s, sample mean for stranger sales, is equal to 281.88 minus 211.43, which is equal to 70.45, so way out here. 70.45. And notice with the alternative hypothesis, this was a two-tailed test because we were looking to see whether or not there was a difference that was either positive or negative between the population means for sales to friends and sales to strangers. So we want to make this a little bit symmetric here. We'll put negative 70.45 over here, and the p-value comes from both shaded regions. So finishing out the test, we have we need our t-score. T-score sub 7.62, that's the degrees of freedom for this bell curve, is equal to the 70.45, that's our sample data, minus the mean of 0 over your standard error of 1870, which is equal to 3.77. Okay, so a p-val here is equal to 2 times the probability, because it's a two-tailed test, that a critical t-score with degrees of freedom of 7.62 would be greater than 3.77. Comes out to be 0.006. So our conclusion, and this will finish the notes, is that due to a low p-val, we reject H0 in favor of H sub A. And there you go. There is the hypothesis test for the difference between means. Have a good one, guys.